Okay, now that we have some of that vocabulary and notation behind us, I'd like to take a minute and compare the existence and uniqueness theorems for linear differential equations and nonlinear differential equations. I'm going to start by rewriting the existence and uniqueness theorem for linear equations on the left-hand side, and then I'll write the existence and uniqueness theorem for nonlinear equations on the right-hand side. And we'll see how, in a lot of cases, at a lot of points, these two theorems are very similar. But then we can talk about the differences, having established what one means and how to use it. We'll talk about the differences between that one and the other one, and then we'll see how to use that. So here's the first one. If the functions p and g are continuous on an open interval between a and b, and containing the point t equals t naught, some value t naught that falls between alpha and beta, then there exists a unique function, we call it y, or we call it phi of t, that satisfies the differential equation y prime, or dy dt, plus p of ty equals g of t for each t in the interval I. And that also satisfies the initial condition y evaluated at t naught is equal to y naught, where y naught is an arbitrary initial value. Now, normally I'd be pointing at these things as my red pointer's working here, but my little hand pointer has stopped working. So I'll use the red pointer for now. We have functions p and g. We have an open interval that goes between a t value alpha and a t value beta, but not including those two values. We have an initial, we have a value t naught. T is equal to t naught, somewhere between alpha and beta. If those conditions are met, then we can find a unique function y equals phi of t that will satisfy this. In other words, that will satisfy this differential equation. In other words, this equation here will be a solution to this differential equation. And that will be the case for every t in the interval I, right? Every t between alpha and beta. And it will also satisfy this function here, this solution, will also satisfy the initial condition that where you plug t naught in for y, here you plug t naught into this function, then it'll spit out y naught. And y naught is an arbitrarily determined or prescribed initial value. That just means that whatever we can set y naught before we even begin looking for a solution to this equation. And I can guarantee that, first of all, a solution will exist and that there will be a t naught that I can plug in, and the result will be the y naught that I was looking for. Okay, so that's what the existence and uniqueness theorem says for first order linear differential equations. Now let's take a look at the existence and uniqueness theorem for nonlinear differential equations. And here it is. Well, most of it anyway. There's a bit missing, but I'm going to go back and fill that in after the fact because I want to compare these as much as like for like as possible. So let's take a look at the one for linear equations first. Actually, let's look at the wording, which is very slightly different but means the same thing. I'm going to look at that first. This theorem says if the following things are true, comma, then these following things are true. In this version, we have assume or let or assign these functions, make these things true, then in that case, these other things will be true. So the wording is slightly different, but it really means the same thing. Okay, now in the linear version, we have two functions p and g, which are both continuous, not necessarily everywhere, but over an open interval. In the nonlinear version, we have two functions, f and the partial derivative of f with respect to y. If that doesn't make sense, make sure you go back and watch the video about notation and vocabulary. So we still have two functions. Remember that the derivative of a function is a function. So we have two functions here, and they're continuous, not on a linear interval, but in a rectangle. I'll come back to that in a minute. But here we're saying the functions are continuous in an open interval, and here we're saying two functions are continuous in an open interval that's rectangular in shape rather than linear. In the linear version, we have in this interval somewhere, we have the point where the value of t is some t naught. T naught is some real, actual numerical value. We just don't know what it is. Whereas t could be anything between alpha and beta. our rectangular version here, our nonlinear version, we are also in this rectangle containing the point t naught y naught. And again, I'll come back and address that in a minute, but the wording you'll see is really very similar. So we're saying the same things here. It's just that the context is slightly different. Now, if those conditions are met in the linear case, then there exists a unique function, a unique solution. Let or assign these things to be true, then there is a unique solution. And in fact, we're even using the same notation here. So as long as these conditions are met, then a function exists that solves this equation. As long as these conditions are met, then there is a function, existing function that solves the equation. Now it satisfies the differential equation that's written here in the linear case, and there is a unique solution of the initial value problem, and that initial value problem is given here in this case. There is one big piece of information missing from this version, and I'm going to come back to that, I promise. But before I do, I want to make the point that in the linear version, the author makes the point of satisfying a unique solution, satisfying the equation first, addresses that situation first, and then says, oh, and by the way, we also get this initial condition. We can find a t naught that will spit out a prescribed value of y naught when we plug it into our solution here. That's all wrapped up in this statement in this case. There exists a unique solution to the initial value problem. We have not only a solution to the differential equation, but also a y naught that we're going to get when we spit out a y naught when we plug in the right t naught. Okay, now before I go in and reinsert the missing information, I want to take a look at what the difference is between this open interval and this rectangle that's talked about in the nonlinear version. The open interval is simply some piece of the number line. We're talking about just real numbers, and somewhere in between alpha and beta, but not including alpha and beta, all of the t values that we're allowed to play with fall between those two values. One of them is called t naught, or t sub 0, our initial input value, which eventually we'll learn would spit out, once it's plugged into the solution, will spit out a y naught value. Okay, so basically I'm allowed to use any value for t between alpha and beta, not including alpha and beta. In the other case, in the nonlinear version, when I say I'm looking at a rectangle, I'm going to look, let me remind you first of all that we often portray three dimensions this way, where this is the corner of a room right here, I guess, and this is the x-axis, this is the y-axis, and this is the z-axis, and we take points in the xy plane and plug them into a function like this one here, has t and y input values, and that tells us what our output value is, which is some value above or below the xy plane. So when I talk about a rectangle, what I mean is some open interval on the xy plane that goes from x equals alpha to, sorry, not x, not xy, ty. The t goes from alpha to beta. And y goes from, we have gamma and delta. There's gamma, there's delta. And what we end up with then is a rectangle between alpha and beta, not including alpha and beta, and between delta and gamma, not including delta and gamma. So in a sense, it's the same as the open rectangle, or sorry, the open interval we were talking about in this theorem, but because we're working in 3 dimensions now, not just 2, our input values have two variables, and we have to be able to pick any point that we want in the xy plane, and that's my input. Now that can have, let's go over here. I could have x equals 1, y equals 2. I keep saying x, I mean t. T equals 1, y equals 2, or I could have t equals 2, y equals 2, or I could have t equals 2y equals 3. I don't have a scale on here, so I hope you're not confused by that. My point is there are multiple combinations of t and y, and as long as they all fall in between t equals alpha and beta and y equals gamma and delta, then I'm allowed to use them. In the same way that I was allowed to use any t value as long as it fell between alpha and beta in the linear case, in the nonlinear case, I'm allowed to use any point t naught, or sorry, t comma y, as long as it falls in this rectangle. So that's what they mean by in some rectangle with these limitations on it. It's just the two-dimensional versions of saying an open interval. Okay, now we're ready to go back and insert that piece that I left out. In this statement right now, it says, then there exists a unique solution, etc. But in fact, we need to qualify that a little bit. Then, in some interval, I'll put it down here, in some interval where t falls somewhere between t naught minus h and t naught plus h. And what that means is that, let's go back over to this version, t, remembered, where is it? Here it is, t equals t naught. This interval I contains the point t equals t naught. So t can be anything between alpha and beta, and one of the things between alpha and beta is this specific value t naught. In this case, that solution is in this interval here. And what this interval is, remember that the white highlighted rectangle here is where the functions are continuous. The solution, which is also a function, is going to fall in some interval. And that interval is defined this way. The t values all come from a range of values, t naught, which is our initial input, t naught minus a number, and t naught plus a number. So let me plot a t naught in here. I'm just going to put it there. Let's call that my t naught. Then this solution, this unique solution, has to be in the interval t naught, I gotta get the right pen going here, t naught minus a little bit and t naught plus a little bit. That pen's not going to do it for me. T naught minus, that's not working either. It's not enough for you to be able to see it. T naught minus a little bit and t naught plus a little bit, or plus a lot. But that interval t naught minus h to t naught plus h is contained in the interval alpha to beta. So this entire interval that I've kind of drawn here, that yellow line there is my t naught. A little bit less than that is t naught minus h. A little bit more than that is t naught plus h. That entire interval still has to fall between alpha, t equals alpha, and t equals beta. So I can't go out here. Even though t naught is inside, if the interval goes outside, I'm not meeting the criteria. The criteria is not a cause, but an effect. In other words, this unique solution that we're going to find here exists in this interval. So not only do we know there's a unique solution, but we know it's in the interval and that it's contained entirely in an interval here, which is itself contained in this larger interval. I did want you to get a really good understanding of this theorem, of both versions of this theorem, but also to see how similar the two versions are. Now what we're going to do is take a look at a couple of examples of how you might use this this nonlinear version in a problem-solving setting. We did that for the linear version in the first existence and uniqueness video, so I'm not going to do that again, but I will do an example of how to find, or how to use rather, the nonlinear version of this theorem, and I'll do that on the next screen. Okay, here's a differential equation, and I am very much inclined to rewrite it before I get going too far on things here as dy dt equals the natural log of ty over 1 minus t squared minus y squared. And what I want to do with this differential equation is to find the rectangle, right? In the linear case, we called it an open interval. We might call this an open rectangle, but the way the problem is worded in the textbook, it says state where in the ty plane the hypotheses of the existence and uniqueness theorem are satisfied. And what that means is to find, I'll do it this way first, to find that rectangle, could be anywhere, we have to do the work to find out, find that rectangle for which this equation might have solutions, right? Hypotheses of the existence and uniqueness theorem state, well, what those hypotheses are, is that the functions f and the partial derivative of f with respect to y, both of those functions are continuous in the rectangle between alpha and beta and gamma and delta. But also that there's a point, t naught, comma, y naught, also in this rectangle, also between where, well, t naught has to be between alpha and beta, and y naught has to be between gamma and delta. That point is on the floor in this rectangle, and that point will be a solution to this differential equation. But it has to be in the rectangle. The criteria we're trying to meet here are that there are two functions continuous in the interval between alpha and beta, and a point also in this rectangle that will be a solution to my differential equation. Now, I don't have the tools at this point to solve this differential equation. This is a nonlinear differential equation, and because of its construction, because of its form, I don't have the tools that I need to solve it just at this point. But that's okay, because that's not what we're asked for here. We're simply asked to find where in the ty plane the hypotheses of the theorem are satisfied. So what we're looking for is, what is this rectangle for this problem? So I'm going to erase this sketch that I have here, and I'm going to resketch it. Before I do that, let me point out that if I just drew the ty plane instead of the tyz plane, then I would have, in this case, I'd have alpha here, looks like, and beta over here somewhere, and then I have delta, gamma, and then delta, right? So I have something that looks like this, and then I have a point somewhere in that rectangle. So what I've done is taken this diagram and shifted it, pushed this axis up here and pull this one so that it's pointing straight out of the screen from you. So right there, and coming right out of the screen at you, is this axis right here. And when I do that, I'm essentially looking down on the floor of the room, and I can see the rectangle. I left some of my shading off. It includes this bit here. I can see the rectangle that I've illustrated here, but I don't really need a third dimension, but I wanted you to see the orientation here. So I'm going to do the second part. I'm going to do the next part of this problem here by just finding the rectangle in this form. I don't need to do it in this form. So I'm going to erase this now. We're going to find the rectangle that applies to this particular problem. Now, we can actually see just by looking at the problem that we've got two issues here. We've got two domain issues. One is that we have a denominator, and denominators can't be zero. And the other is that we have a log expression, and the argument of a logarithm has to be strictly greater than zero. It can't be zero, and it can't be negative. So I'm going to tackle these separately. One is that I'm going to say that the argument of my log has to be greater than zero. And over here, I'm going to say that my denominator, 1 minus t squared minus y squared, has to be non-zero. It has to not be equal to zero. Well, here there's nothing really to solve, but I can take a look at some cases, if you will. clearly t can't be 0 and y can't be 0, because if either one is 0, then this product is 0 and that's equal to 0, and this ty must be greater than 0. This argument cannot be 0, it has to be positive. Also, since t and y, the product of t and y has to be positive, either both t and y have to be greater than 0, or both t and y have to be less than 0. If the product of two positive numbers here, a positive times a positive, that's positive. If I have a negative number, if t is negative, then y must also be negative so that the product of those two is still positive. So these 4 statements are all necessarily true in order for this to be true. And this statement right here comes from the fact that my log has to have a positive argument. Very, very quickly, the reason for this is, let's say we have the natural log of, let's go with k. I'm looking for a different variable here. And I'm going to call that y. Y equals the natural log of k. If I exponentiate this, exponentiate both sides, I get e to the power of y equals e to the power of the natural log of k is just k. Okay, if k is a negative number, if this is negative, then I have e to a power equals a negative number. But e to any power, no matter how small the power is always going to be positive, right? So this equation has no solution, which means this number right here cannot be negative. So you can't take the log of a negative number. Equally, it never equals 0, right? So this can never be 0. This can never be equal to 0. So k cannot be 0 either. Okay, so we've established the qualifications for our numerator to be defined, right? The log has to have a positive argument. So now let's take a look at the denominator. Let's find the values of t and y that make this true. And that is, it's tempting, I think, to solve this for y and then take the square root of both sides. But I'm not going to do that. Instead, I'm going to add t squared and y squared to both sides, and I get 1 equals t squared plus y squared. Now this is a denominator, so it actually has to be non-zero. So I'm going to remember to write my equality symbol as a not equal to. And then I'm going to switch sides, just sort of to help you see what's going on here. Lastly, I'm going to replace this with an x, not because that's what you should do in this case, but to help you see. Let me take the equals out, the not equals out of there for just a minute. This is the equation of the unit circle. Okay, x squared plus y squared equals r squared, where r is 1. And what I'm finding here, let me go ahead and circle that as well. This has to be true. Well, I'm not going to circle that one, actually. Let me erase that one, because that is in terms of x. And my differential equation is in terms of t. So get that highlighter. This statement is, this is how I set this up. And then this is the criteria that has to be met to make this original statement true. So these criteria, these restrictions, and these restrictions, or this restriction, they must all be true. So what I want to do now is take a look at what this looks like on the graph. Let's find all the places where t and y are greater than 0, but neither one of them is equal to 0. I think I'll use a highlighter for this as well. If t and y are both positive, and then we're going to get all of the first quadrant, right? All my t values, all my y values are positive, not touching the x-axis or the t or the y-axis here. Or if they're both negative, so then I'm going to be in quadrant 3. careful not to touch I kind of touched the axes there. You'll have to pretend with me that didn't happen. Okay, now these go on forever in these directions, right? Those are supposed to be arrows. I'm using a fat pen. So these are the places where I am allowed to select points T. Oh, let me use a different color. That is not going to work for us. That pink is too hard to see. I'll use this yellow one. Here's a point T. I'll call it T1, Y1. Okay, there's a point in this area, T2, Y2. These points are all allowed. These points are all in the domain of this function, which is a derivative, right? This function is a derivative of another function, this function right here. And the points that I'm allowed to use for this as input values for this function all fall in quadrants 1 and 3, but not on the axes, only bumping up against the axes. That takes care of this set of criteria. Not on the axes comes from these two inequalities, and this is quadrant 1 and this is quadrant 3. Now let's look at this one. Since this is the equation of the unit circle, I'm going to put some unit markers down here. Each of these is 1, so there's a 1, -1, there's a -1. And then I'm going to draw the unit circle, but in this case, I had, these are the places where the t and the y values are allowed, right? These are the t and y values I'm allowed to use. I'm not allowed to use 0 for either of them, so I didn't mark the graph showing that I was touching the axes. With this other restriction, though, I'm going to have to use, I could color in the entire graph except for the unit circle, but that would be really quite difficult to do. So I'm going to color in the unit circle. I'm going to draw the unit circle, but I'm going to use a different color. I'm going to use this red highlighter to sort of help to indicate this is where you're not allowed to work. Drawing circles is hard. You get better at it with practice, but even so. And that's kind of hard to see. Let me just go ahead and put, I'll draw over it with a darker pink there. So these are non-allowed values. I'm not allowed to choose any values from the unit circle. So where am I allowed to work then? I'm allowed to take any values I want from, let's see, what color should I use this time? I think I'll stick with yellow. I can pull values from here, or here, just not on the circle, or here. Trying to be really careful here, not to touch the axes, not to touch the circle. It's hard to do. Okay, and again, going off infinitely there. So where you see yellow, now yellow highlighter, is all the places where I'm allowed to pull points that will satisfy or potentially satisfy my differential equation. Trying to kind of complete this here. There, I decided you didn't need to watch me do that. So you can see I've missed out the points that fall right on the unit circle. I've missed out all of quadrants 2 and 4. I've missed out points in this quadrant that touch the unit circle. I'm only bumping up near the unit circle, right? So where you see yellow is where I'm allowed to pull points from for the solution of this problem. Now, this is not a rectangle, but when I find my specific solution, let's say it's here, T naught, Y naught, I will be able to establish a rectangle around this point that is, I just missed that. actually, it's okay. I'll go like this. Now it looks like I'm cheating here because it kind of looks like I'm getting some t-values that are inside the unit circle that are on the unit circle, right? But I'm not, because the rectangle I'm actually ending up with is this rectangle here. I hope you can see that. It's not ideal. I wonder if a different color would be better. Now it's just getting darker. So I have found a rectangle, and that means that I can tell you what my alpha and beta, gamma and delta values are. And if I needed to, I could also find a value for h to say that around this point, there is an interval in which the solution to my differential equation, which will be a function, lives. Again, I'm struggling to find a pen color that actually does the job here. This function here that I've drawn in this interval between, there's my t naught, y naught. So t naught minus h and t naught plus h. There's a function that goes through that point that is a solution to my original differential equation. It probably doesn't look like this. I've just drawn a generic function. But that function is a solution to my original differential equation. And not only does the point live in this rectangle, but the graph has a domain that lives entirely inside the rectangle as well. That's what the second theorem says, the existence and uniqueness theorem, the one for nonlinear equations. That's essentially what we're getting at here. And so what we have done is we have, in fact, found where in the xt plane the hypotheses of this theorem are satisfied for this particular function. How would you write this? Well, I kind of abbreviate what I've got written here. I might say, for example, that 1 minus t squared minus y squared has to be greater than 0. 1 minus t squared minus y squared has to be less than 0. And t cannot equal 0 and y cannot equal 0. This isn't the only way to write this, but this expresses the idea here. 1 minus t squared minus y squared is greater than 0 outside the unit circle. 1 minus t squared minus y squared is less than 0 inside the unit circle. And because neither of these has an or equal to line underneath it, the actual unit circle, the points that create the unit circle, are left out here. So all the points outside the unit circle, all the points inside the unit circle, but also t cannot be 0 and y cannot be 0. We're not on the axes here. And finally, the product ty cannot equal 0. That is how we leave out quadrants 2 and 4 by virtue of, let's see, where am I? By virtue of this work that we did down here. Here we were just making an observation, but here what I'm trying to do is create like a shortened list of solutions here. We might use set builder notation or something equivalent to it. This is a set, this is the set of all the places from which I can pull points in the ty plane. All the places outside the unit circle, all the places inside the unit circle, as long as t and y are not 0, and as long as the product of t and y, just realized I meant to write a greater than there. Pen's not working, here we go. T and y, the product of t and y has to be greater than 0. That comes from the log of ty, this argument for the log has to be strictly positive. So that's how I'd write the solution to this question, or the answer to this question. We have not solved this equation. We have simply found the rectangle in which solutions exist, in which the hypotheses for the theorem are satisfied. I had another sort of lengthy example planned for this last slide, but I think I'm just going to stick with something really quite simple. I want to go over the example in the textbook, y prime equals y squared with the initial conditions y of 0 equals 1. And the main reason for this is that we're not going to see a lot of nonlinear equations, so I don't really want to spend a lot of time on it, but I do want to take the opportunity to talk about the theorem as it applies to this problem. We're going to be solving this initial value problem. Initial value, sometimes you see this abbreviated IVP, initial value problem. And we're going to determine the interval in which the solution exists. So let's start with by finding the solution. This is a very simple nonlinear differential equation. I'll start by writing it as dy dt instead of y prime. Now in this particular case, there is no indication on the right-hand side whether the variable that I've been asked to work with here, the independent variable, is x or t. So I've sort of just randomly chosen t. Also, that's what this example in your textbook uses. I'm asked to solve this problem, but I'm also asked to determine the interval in which the solution exists. Because of where we are in the textbook, I want to take the opportunity to show you that how the theorem that we've been talking about applies here. We want to look at our two functions. First of all, our function f, which is a function of t and y, is the right-hand side of my differential equation. Okay, and that, if we were to graph that, I can't draw a straight line tonight. There's t, there's y. This is just a parabola. Okay, it's continuous everywhere. If I start up here at negative infinity or out here at negative infinity and start graphing, then I'm just going to graph and I never have to pick up my pen. So this function is continuous everywhere. The derivative of this function, the partial derivative of the function f, taken with respect to y, is 2y. That's just a line. And that is also continuous everywhere. Okay, so both of these functions are continuous everywhere, in which case the criteria that our two functions, f and the partial of f with respect to y, are continuous, that criteria is met. Now technically they only have to be continuous in a rectangle, but because we know that they're continuous everywhere, at this point our rectangle is infinitely large. Okay, the next criteria is that a point t naught y naught is in that rectangle, and that point t naught y naught is given by our initial conditions. I could write this way, or I could write it 0, 1. And there's my t naught y naught. And that point, 0, 1, is, well, about there, I guess. Kind of hard to say what the scale on this thing might be. That is in my infinitely large rectangle. So that point is in my rectangle, so that criteria is also met. That means that this thing right here, or this thing right here, if you want to write it this way, has a solution, and that the solution to the initial value problem is unique. There's only one. All right, so now that we know it's worth taking the time to try to find the solution. Let's go ahead and do that. I'm going to write this as, or treat this as, a separable differential equation, which it is, which means I can write this as dy over y squared. I'm going to write that as y to the negative 2 dy, and that's equal to just dt. And when I integrate both sides, I get y to the negative 1 over negative 1 equals t, and then of course plus a constant. This term is negative. I'm going to rewrite y to the negative 1 as 1 over y. I'm going to push that negative 1 through the entire equation, so I get this. And then there's a nice little property in algebra that says if you have a over b equals c over d, you can flip both of those ratios over and you get b over a equals d over c. I'm going to apply that here by saying 1 over, I'm going to use different letters here, 1 over k equals p, pretend that p is p over 1, that means that k over 1 equals 1 over p. And I'm going to apply that to this statement here. So I'll get y equals 1 over the right-hand side, but the whole right-hand side. And that's my general solution. Let's go ahead and highlight that. That's the general solution to this differential equation, but I've got initial conditions. So let's go ahead and apply the initial conditions. The initial conditions are that when t is 0, when I plug a 0 in there, I get for y, I get 1. So now I'm going to solve this for c, the only unknown value left. Let's put this up here. If I multiply both sides by, well, this is just going to be 0, right? So this is going to be 1 over negative c. If I multiply both sides by negative c, I get negative c equals 1. Therefore, c equals negative 1. And then I'm going to take that value for c and plug it back into my general solution. So I get y equals 1 over negative t plus 1. Obviously, a negative 1 is positive 1. And I could write that way, or I could write it as 1 over 1 minus t. Kind of doesn't matter, but I don't know. We really like those leading numbers to be non-negative whenever possible. Just feels a little tidier. Now we have a problem, though. This is a denominator. Denominators can't be 0. So 1 minus t can't be 0. So 1 cannot equal t. T cannot equal 1. Therefore, I have a line, vertical line here at 1, this is the line t equals 1, on which the solution we found here, that solution is undefined at t equals 1. This won't come as much of a surprise because we know that this solution, when we graph it, looks something like this. Right? It's a reciprocal function. We know our function is undefined at t equals 1. We know in this case that the solution goes through the point 0, 1, which is the initial conditions we were given. So that's, again, not much of a surprise. But we don't want the entire graph of y equals 1 over 1 minus t. We want the part of the graph, or the part of the function, the part of the domain that satisfies this equation with these conditions. And so since I have to define a rectangle, I need lower and upper bounds on t, and then also lower and upper bounds on y. And t, we can see, goes up to 1, but does not include 1. And there's no lower bound, so we have negative infinity. On y, we can get all the way down to 0, but there's no upper bound, so we have positive infinity. So our rectangle goes from negative infinity to 1 for t, and for y, we go from 0 to positive infinity. This is my alpha, this is my beta, this is my delta, and this is my gamma, and this is my delta.